With this video, we begin our unit on Chapter 15, entitled Acid-Base Equilibria. In this unit, we consider the topics that we covered in Chapter 14 in much greater detail. You can think of this as sort of being advanced topics in acid-base equilibria. As I've done in the past, I'm jumbling the order of the units in the textbook a little bit in a way that I think makes more sense to me, so let's go over a quick outline. We'll begin with Chapter 15.1 in this video, discussing solutions of acids or bases that contain a common ion, and I'll define what that means in a second. We'll jump ahead to Chapter 15.4 to talk about titrations and pH curves, a way of analyzing what happens during the titration of an acid with a base or vice versa. And that leads us to a consideration of acid-base indicators, why we choose a particular indicator for a titration. We'll then go back and consider buffered solutions in Chapter 15.2 and finish by talking about buffering capacity. So let's begin. Solutions of acids or bases containing a common ion. So let's consider the prototypical ionization of a weak acid, HA, in equilibrium with H plus A minus, for which we can write the Ka expression, H plus A minus over HA. The question we ask here is, how is the ionization of this weak acid Ka affected by the presence of a common ion, that is, a product of the ionization? Or stated more explicitly, how will the extent of the ionization of the weak acid be affected if, rather than carrying out the ionization in pure water, we carry out the ionization in the presence of a substantial concentration of one of the products of the ionization? Well, we would predict, based on Le Chatelier's principle, that the presence of this ion, A minus, the conjugate base, would shift the equilibrium toward the reactants. That is, it would suppress the ionization of the acid. Well, let's look and see. We can do the calculations. Let's find out. So, here let's calculate the pH and percent ionization of a 1 molar solution of hydrofluoric acid, for which Ka is given, and then a solution containing both 1 molar hydrofluoric acid and 1 molar sodium fluoride. What is the significance of sodium fluoride? Again, sodium salts are soluble, so this will be a 1 molar solution of the sodium cation plus the 1 molar solution of the fluoride anion. We don't care about the sodium cation, it's just a spectator ion. The significance is that now we have a substantial concentration of the conjugate base, a common ion, one of the products of the ionization. So, let's do the calculations. So, HF is in equilibrium with H plus F minus, for which I can write Ka as the product of the hydrogen ion concentration, the fluoride ion concentration over HF is 7.2 times 10 to the negative 4th. I'm going to skip the ice table and just jump ahead to what we know we're going to do anyway, which is Ka equals x squared over 1.0 minus x equals 7.2 times 10 to the negative 4th. We will, of course, make the simplifying approximation, which leads to x is equal to the hydrogen ion concentration is the square root of the initial concentration of hydrofluoric acid times Ka, or 0.027 molar with a unit. My pH is the negative base 10 logarithm of 0.027, or 1.57. Kind of feel like we've done this same problem before. And my percent ionization is the concentration of hydrogen ion produced in the ionization divided by the initial concentration times 100, or 2.7% ionization. So now, let's do the same calculation, except instead of having it occur in pure water, we'll have the ionization occur in a solution that already contains 1 molar concentration of the fluoride anion. Well, let's do the ice table just for fun. My initial concentration of HF is 1. My initial concentration of the hydrogen ion is approximately 0. But now my initial concentration of fluoride ion is also 1 molar. Minus x plus x plus x, 1.0 minus x, x, 1.0 plus x. My Ka expression now, instead of having x squared in the numerator, has the concentration of hydrogen ion times the concentration of fluoride ion divided by the concentration of hydrofluoric acid, which is 7.2 times 10 to the negative 4th. I can immediately see that both of these expressions in the numerator will cancel, and that leaves me with a value of x equal to 7.2 times 10 to the negative fourth molar as my hydrogen ion concentration. So the pH now is negative base 10 logarithm of 7.2 times 10 to the negative fourth, or 3.14. And my percent ionization is 7.2 times 10 to the negative fourth molar over 1.0 molar hydrofluoric acid times 100, or 0.072% ionization. As you can see, this is a pretty substantial difference from what we calculated in part A, so let's summarize. 1 molar hydrofluoric acid is 2.7% ionized with a pH of 1.57. 1 molar hydrofluoric acid plus 1 molar fluoride, a common ion, namely the conjugate base of the weak acid, is only 0.072% ionized with a substantially higher pH, 3.14, corresponding to a lower equilibrium concentration of the hydrogen ion. So what we see is that the ionization is suppressed by the presence of the fluoride ion, a common ion, which we can explain using the Chatelier's principle. And the important point is, in these calculations, you can always make the simplifying approximation. X will always be negligible relative to the initial concentration of acid or base. Okay? So we write the Ka expression, and what we find is that the equilibrium concentrations of the acid and the conjugate base are always equal to the initial concentration. Again, I can't emphasize strongly enough, any further ionization in the presence of a common ion is negligible. What we find is that the pH depends only on Ka and the relative concentrations of the acidic component and the basic component. And given any three of the variables in this Ka expression, we can simply rearrange, plug in, and solve for the fourth. So here's an example. A solution of acetic acid, for which Ka is given, and potassium acetate, which contains the acetate anion. The conjugate base of acetic acid has a pH of 5.0. What is the ratio of the concentration of acetate anion to acetic acid in this solution? As we will see in the next unit, the ratio of conjugate base to acid, or vice versa, is an extremely important quantity. So I'll begin by writing out my Ka expression. Right. I will abbreviate acetic acid as HA and acetate as A- for convenience. Since I'm trying to find a ratio of acetate to acetic acid, I will simply rearrange to isolate the concentration of acetate over the concentration of acetic acid. That gives me Ka over the hydrogen ion concentration, 1.8 times 10 to the negative fifth, divided by, given the pH of 5, so the hydrogen ion concentration is going to be 10 to the negative 5.00, and that gives me a value of exactly 1.8. Now, this is important because this tells me in any solution that contains a ratio of acetate to acetic acid, a ratio of 1.8 will always have a pH of 5.00. It doesn't matter what the absolute concentrations are, as long as the concentration of acetate is 1.8 times greater than the concentration of acetic acid, I will have a pH of 5. Now, what about the ionization of bases? Do we have the same thing going on? Well, let's try it and see. For an ionization of a weak base, I can write the equilibrium. The base plus water is in equilibrium with the conjugate acid plus hydroxide, for which Kb is equal to the concentration of the conjugate acid times the concentration of hydroxide over the concentration of a ionized base. So, how would the pH and the percent ionization of the base be affected by the presence of the conjugate acid? Well, based on what we saw before and what we inherently understand, we would expect that the ionization would be suppressed by the concentration of BH+. Well, once again, let's do an example and see if that actually is the case. Calculate the pH and percent ionization of a 1 molar solution of ethylamine for which Kb is given. and a solution containing 1 molar ethylamine and 1 molar ethylammonium chloride. Once again, I expect you to recognize that this formula represents a solution containing the ethylammonium cation plus the chloride anion simply as a spectator, which is irrelevant. So, once again, let's do the calculations, and I'll skip some stuff here for simplicity. I'm going to write Kb equals BH plus OH minus over B, which is x squared over 1.0 minus x equals 5.6 times 10 to the negative fourth. I will again make the simplifying approximation. X is equal to the hydroxide ion concentration, which is equal to the square root of the product of the initial concentration of the amine times Kb, or 0.024 molar, as my hydroxide ion concentration. My pH is 14.00 plus the base 10 logarithm of the hydroxide ion concentration for 12.37 as my pH. And to calculate the percent ionization, .024 molar hydroxide over 1.0 molar ethylamine times 100 is 2.4% ionization. Now, for part B, let's consider the following. My Kb expression is the same, but now my concentration of the ethylammonium cation, the conjugate acid produced in the ionization, is the initial concentration plus the further ionization, divided by 1.0 minus x, or 5.6 times 10 to the negative fourth. Once again, the simplifying approximation is valid, and I obtain that x is the hydroxide ion concentration equals 5.6 times 10 to the negative fourth molar. My pH is 14.00 plus the base 10 logarithm of the hydroxide ion concentration, or 10.75. And my percent ionization is 5.6 times 10 to the negative fourth molar divided by 1.0 molar times 100, or 0.056% ionized. So, once again we see that the presence of a common ion, in this case the conjugate acid of the weak base produced in the ionization, significantly suppresses the ionization, i.e. it shifts the equilibrium back towards the reactants, resulting in a substantially lower percent ionization, as well as a lower pH value, indicating a lower concentration of the hydroxide ion. So, works for bases as well. Now, let's summarize. Here's an important point. Suppose I have a solution, and all I tell you is it has both ammonia and ammonium. Which ionization equilibrium should you consider? Well, you could consider the weak base ionization of ammonia, producing ammonium plus hydroxide, as governed by the Kb expression, and the numerical value of Kb. Or you could consider the weak acid ionization of ammonium to form ammonia plus the hydrogen ion, as governed by the Ka expression and the corresponding value of Ka. So the question is, and this is kind of an important question, which one of these two equilibria should you consider? Well, I'm going to say this literally 10,000 times in this unit. It doesn't matter. It makes no difference whatsoever whether you consider a solution of ammonia and ammonium as being governed by the weak base ionization of ammonia as governed by the Kb expression, or the weak acid ionization of ammonium as governed by the Ka expression. It makes no difference whatsoever. as long as you pick one of the two ionization equilibria and the correspondingly correct equilibrium expression and equilibrium constant, you will get the same answer. Choose whichever one is more convenient. Okay, so once again, I'll say this literally 10,000 times, stop thinking of this as a solution of a weak acid and its conjugate base or a weak base and its conjugate acid. Instead, think of it as an acid-base conjugate pair. Once again, choose one of the two equilibrium ionization expressions and stick with it, and you'll get the same answer. Okay, so the ionization of a weak acid or weak base in solution is suppressed by the presence of the product of its ionization by Le Chatelier's principle. And the calculation of equilibrium concentrations is easy because we can always make the simplifying approximation, simply rearrange the K expression to isolate whatever you're trying to find, and X is always going to be negligible in comparison with the initial concentration. So what's up next? In the next section, we'll talk about what a titration curve is. A titration curve is a graph of pH as a function of volume of titrant added when you are titrating a weak acid with a strong base or a weak base with a strong acid. And then after that, we'll talk about buffer solutions. A buffer solution is a solution containing similar concentrations of an acid-base conjugate pair that resists the change in pH when you add external strong acid or strong base. So we'll see you then.